can do with, there's two types of calorimetry we'll talk about: isothermal titration calorimetry and differential scanning calorimetry. Both of them will be introduced today in sort of a intro light flavor. And then in chapters 10 and 12, respectively, we'll do them in much more detail. Okay? So ITC, a useful tool for studying the thermodynamics of biomolecular interactions. Okay, so what we have here, these pictures are sort of showing the same thing. I have a reference cell, and then I have a solution of interest. So in here is probably something like water with my proteins in it, and this is just water. And then I have a syringe filled with whatever I want to bind to the protein, whatever I'm interested in. Okay? And I'm going to drip it in and capture what happens in terms of heat change. Okay? Slowly titrate in a small aliquot of ligand, wait for equilibrium between each. Okay? So give it enough time, then put in more. Give it enough time, put in more. Keep the cells at constant temperature, so that's this isothermal piece. The titration piece is sort of this sort of slow addition of our whatever's binding, our small molecule. And then so what we're actually measuring is the heat change. I want to keep these two things at the exact same temperature, and when I drip something in here, I expect heat to come out. So what the instrument is telling me is how much heat I had to pull out of my sample cell to keep it the exact same as the water where nothing was happening. And I drip in more, and again, I have to pull heat out, and I drip in more, and again, I have to pull heat out. Okay? And what that data is going to look like is something like this. This is calorie. I will give you the definition of calorie on a future slide, but another useful energy unit. Okay? So we have microcalories per second here. So again, each of these lines is correlating to one of these times I'm titrating in some of my ligand. These are all negative because, again, I had to pull heat out of my system to keep the two temperatures identical between the water and the water with the protein, since in this case, something's actually reacting. A zoomed in view shows that if you integrate under all of these peaks and sum them up, you'll get total heat. This part you don't have to know at all yet. Don't worry about it. It's forthcoming. Okay. But again, because I can integrate all these little peaks that I get and sum them up and get the total heat that was released through this entire experiment, I can talk about a total enthalpy or total internal energy change when these two things are reacting. These are two good links about ITC that I would recommend. Okay. So this is the exothermic reaction. Can I use ITC for an endothermic reaction? And if so, what does the data look like? Flips over, positive now. Yeah, sure, some stuff will react and it draws in heat. It's an endothermic reaction. So again, then the instrument is supplying heat to that cell to, again, just keep them at the exact same temperature the whole time. The reference cell is really doing nothing but sitting there and monitoring its temp, whatever you preset it to. And the other cell is doing all the work. Do I have to put heat in or take it out to keep the temperature matching? And that's all that we're doing.